Good evening, everyone. So this is session 11, and the final session will be session 12, and there will be an extra session after that week. So let's begin our session 11. So we were discussing about the electrical properties and bits and pieces about magnetic properties. So I will be explaining some briefly few topics and also some question and answers, so that you people can perform well in your assignments. And also I will be dealing with some of the derivations which will be helpful in your homework assignments. So let's begin with magnetism. Where the magnetism arises and what is the source for magnetism in materials. And there are different types of magnetism in materials like ferromagnetism, paramagnetism, that we will come in a bit. But where it actually arises. So there are three parts for the magnetism. Two parts from electrons and one part from nuclear spins. One is from nucleus. And there are also other minor spins, but somehow we are neglecting them. So there are three parts, and the two parts are from electrons and one part from nucleus. So again, what are the two parts from electrons? So one is from orbital motion of electrons, or orbital movement of electrons in an orbital. So the next one is intrinsic spin of electron. Right? So intrinsic spins of two types. Electron will have either spin up or spin down. Right? These are the two intrinsic spin of any electron in any atom. So the last one is the nucleus one. It arises from neutrons. And again, intrinsic spins. Again, this part is very negligible from nucleus, so it goes down to 0. I mean, if you're talking about at room temperature, right? So it is negligible, and also the dominant the magnetism coming from is from the intrinsic spin of electrons. This is the main part. Again, so now we know where the magnetism is coming from, right? So again, so how what is the value that we define to any, like what is the quantization, or what is the quantity of any movement of electrons, right? So we define a term called magnetic moment. So let's just follow with the orbital motion, also not the orbital motion, or the orbiting of an electron in an orbit. So let's take that case for the simplicity, right, to understand. So we know the current I is equals to Q by T, or we can even in classical way we can define it as a Q by T, and also in pure mathematical differential form we can represent current as the rate of flow of charge. So now, if you are talking about a nucleus and electron is revolving around, right? So and we represent this distance between is r, the radius. So now we know time is equals to 2 pi r by v. So we know the basic mass, where the distance, total distance, equals to 2 pi r, which is the circumference, by divided by velocity, which is the velocity of the electron. So now coming to magnetic moment. What is magnetic moment? Magnetic moment equals to I into area, or the area of the loop, right? So this. And which is the area of the loop. So mu equals to minus E by 2 pi r into v into pi r square, right? So this will be equals to E by 2 pi by s cancel, and if I multiply, so it will be equals to v, and r gets cancelled, it will be v cross r, v times r, right? So continuing it, magnetic moment equals to minus, now again dividing by mass on both sides, E by m times 2 m into, let's write in vectorial form, which will be v dot r, right? So we know mv is momentum, dot r will gives us the angular momentum, right? So this will turn out to be minus E by 2m into angular momentum. So this is our magnetic moment arising from angular momentum. Well, in quantum mechanics, L is called as a angular magnetic moment. Right? We have the principal quantum number. Next, we have azimuthal quantum number. We have then magnetic quantum number and spin quantum. Right? So this tells us the azimuthal quantum number. This is the azimuthal quantum number. Now, it is from the motion of electron around around the nucleus. This is derived from a classical way, and we can even derive a quantum mechanical model, but to approach the same values, we need to multiply it with a constant, which is called as g. Now q is our mass of electron. Now what is g is the Lambda g factor. We can derive that Lambda g factor, but it is not it is out of scope for this course. So now that is magnetic moment coming from the orbital magnetic or azimuthal quantum, right? The orbital magnetic moment. One is the orbital magnetic moment. Now the same comes from intrinsic spin. We can write which is spin equals to Lambda g factor gs times charge of electron divided by 2 times of mass of electron into s. S is our magnetic quantum, right? And this E by m is also called as magnetogaric ratio. Now we experimentally measure to define S, and we go indirectly to find magnetic moment, and G is approximately equals to 2 from Lambda G factor, right? So if I try to write the total magnetic moment from the orbital side, also from spin, then it will be equals to mu s plus L equals to G times, if I take G equals to 2, then Q by 2 mass of electron MC times L plus S. This is from both the orbital magnetic moment and spin magnetic, right? And now this is one case, and this is only purely arising from the material itself. Now there is another thing that we are missing, that is the Zeeman interaction. What is Zeeman interaction? Zeeman interaction is nothing but the interaction of a magnetic spin, or the spin of an electron with the external magnetic field. So the energy associated, or the energy with the Zeeman interaction, is equals to minus mu dot B, where mu is a magnetic moment and B or H. If you are talking about in vacuum, you can take just H. If you are talking about the magnetic flux, that magnetic flux is phi, the magnetic field induction, then you need to take B. So it's better to take B rather than H to avoid the confusion. So it will be equals to mu b cos theta minus mu b cos theta, right? So now, if what happens if our magnetic moment and B are in opposite directions, then that will be positive. So that's magnetic fields will try to align in the B direction. Why? To minimize this E energy, right? The Zeeman energy. Now, from here we try to go to the paramagnetism, right? So to know the paramagnetism, another term. One is what we have defined two terms. One is the magnetic moment. Another way is the energy, the Zeeman interaction energy. And the third term that we are going to define is the magnetization. What is the magnetization? Magnetization is a macroscopic quantity, but whereas the magnetic moment is a microscopic quantity. Or you can say it talks about the spins, single spin, right, or the single electron, but not the case for magnetization. So to write it more classically, we can write it as a quantity which corresponds to the bulk material, not the intrinsic property, and it equals to the vector sum of, if we write it, M is equal to the total magnetization of the material equals to the vector sum of all moments magnetic moments divided by the volume of the material. So to avoid the magnetization depending upon as a dependent quantity, we divide it by volume so that it remains independent with respect to the volume of the material, right? So that is about the magnetization. Now coming to the paramagnetism. Now the first thing that comes from the material, or the first thing we take from the material is, so now coming to the material, so we define magnetism as the response of any material to the magnetic field. That's how we differentiate different materials in terms of magnetism, right? The first one is the diamagnetic material. The question is, what is diamagnetism? I will not go deep into it, but I will just write an equation so that you can understand. We all know Schrodinger equation, which contains one, the kinetic energy term, which is p square by 2m, and another one is the potential energy term plus the Zeeman interaction term. Now, these are the two terms. Now, if you want to add more, then the p square term will have p plus E. A is the potential, right? The magnetic potential. Just the electrostatic potential, we have the magnetic potential. You can represent as that. So, if I try to reduce this equation or simplify this equation, it will turn out to be. This equation will have a term. One is the H naught, the ground Hamiltonian or the zero order Hamiltonian, which contains the momentum value, which contains the kinetic energy term, plus if we have B, then we have a Zeeman interaction. If we have some potential, the potential is always there because we have a nucleus, right? So we have protons and neutrons. And the protons provides the electron potential, so we already have it. So that is a ground or zero order Hamiltonian. Plus we will have a value, we will have a constant C1 and B cross R. And this term, and there are other terms. One is the Zeeman interaction term, and there are the other terms coming from the magnetic moments, right? The magnetic moment from orbital and spin, that will come here. One is Zeeman interaction, and the third one is the diamagnetism part. So this part is very important because it defines the diamagnetism. That means the diamagnetism is an intrinsic property of any material, right? I will come to that in a minute. Now, why I am calling it as an intrinsic property? Because every spin, right? If you are talking about, let's say there is you have a material. Let me know. Yeah. Suppose this is my material, a 2D sheet. We have number of spins here. Let's say they are pointing in one direction, and the basic assumption is that, let's say, they are not interacting, and that is the case for paramagnetism. Okay? So that's how we get the paramagnetism here. Now, coming to the diamagnetism, every spin has this character B crossover. Right? If you are writing for a single spin, then this term is there. Now, so every material will have a diamagnetism property, but the other magnetisms, which are like ferromagnetism, which will come into it, or the paramagnetism, they mask this diamagnetism. So please remember this, the diamagnetism is an inherent property of any material. So every material or every spin will have this B cross R value, right? But the other magnetisms, the other properties dominates this diamagnetism. That's why we don't see the diamagnetism in many of the materials, because the other phenomena dominate this diamagnetism. So that is one point. Now, it's like masking the diamagnetism. Now, coming to the paramagnetism, right? So the basic assumption of the paramagnetism is each spin is free to move. Free to move. I mean, it can align in any direction. So it has a freedom. But I mean, it has a freedom to align in any direction. That is one. Two. Now, every spin doesn't interact with others. Doesn't interact with others. So, let me tell you again what are the assumptions in paramagnetism. Each spin is free to move, and every spin no spin interacts with each other. So, currently we are talking about the non-interacting spins. Ideally, that is not the case ideally that is not the case in ferromagnetism or other spins. But to simplify and to go through that behavior. So to understand that behavior, these two assumptions are important. So let's say if I have a material in which there are n number of plus half spins, and also there are n minus half spins, right? Let's say they are not equal, n plus half and n minus half not equal. So let's define these terms. Let's say if I write, if I am taking about like, if I am writing the plus half in quantum state, I can write it as alpha. Let's say minus half, then I can write it as a beta. Please don't, this is just a representation of any quantum state. So please don't mind these ones. They are useful to represent any state. Like if I represent to plus half, I will represent of alpha. I can just represent it as like this, right? But just for simplicity, not making more number of diagrams. So for simplicity, I am just assuming alpha and beta. Let's write alpha again, taking the Boltzmann statistics. So exponential E alpha energy by kBT. The same goes for n beta. I will not be simplifying everything, so you can just do it. These are just simple mathematics problems. So another thing, there is a partition function. So what does the partition function have? Partition function has the both terms. I mean the total term. So it will be n alpha plus n beta. This is a partition function. Now what is that? So Now again, for simplicity, let's talk about only electrons. We can even define for any spin or any different. Let's say if I have a half spin time, I can even take for a 3/2 spin time. So it's on for simplicity. Let's stick or let's consider only the electron case. So it will be mu b dot b for positive half, mu b dot b. This is for negative half. Then what is the partition function? The exponential e power x plus e power minus x. That is the cosh function, right? So it is not exactly cosh. It is a hyperbolic cosh function. So mu b b by k by t. Now what is n alpha? N alpha is exponential mu b b by k by t divided by partition function, which is 2 cos h beta. Now, what is magnetization? What is the total magnetization? As I have said before, coming to m net or mt, the total magnetization of a material, which is a microscopic property, right? Then that is, as I have defined before, that is a vector sum of all the magnetic moments divided by volume. So that will be equals to n times mu b, where n is the total number of electrons, times and because I am writing as n alpha minus n beta, so that is my e power x minus e power minus 6. That will be equal. That is our tan h, right? Sorry, e power x minus e power minus x divided by e power x plus e power minus x. That is our tan h function. It is a tan hyperbolic function. So mu dB by k by t. Now m equals to n times mu b, and again we can just use this equation and we can draw, but to derive the paramagnetism or to know the Curie's paramagnetism law, so let's do the high temperature approximation. In high temperature approximation, what do we take? We take k by t is very much greater than mu bb. That means x is very much less than 1. So finally our m will be m equals to n mu b square b by k by t. This is our magnetization. Now what does that mean? This means the magnetization is inversely proportional to temperature, right? And from m we can derive susceptibility. M is directly proportional to susceptibility. M is equals to susceptibility times h, magnetic field intensity, right? So susceptibility is inversely proportional to temperature. This is the Curie's law of paramagnetism, right? If you want to, this is a simple one. If you want to know what type of magnetic material it is, just perform the experiment, the magnetization versus temperature, right? It tells about the susceptibility, and which in turn tells about what type of magnetic material it is, right? So now if I draw the susceptibility magnetization versus temperature, it is inversely proportional. I mean the magnetization is dropping with respect to temperature. It goes to 0, then that means it is a paramagnetic material, right? So that is about paramagnetism. Now moving on to so the first assumption was there is no interaction. First there is a diamagnetism, which is an inherent property. That term goes B cross R. That comes in every spin. Whatever atom you take, that is inherent property. So put it aside. The next one is a paramagnetism, which masks the diamagnetism. What is paramagnetism? Paramagnetism, again, the spins are not interacting. Now moving on to ferromagnetism. Now here the assumption is not the assumption. The true case is the interaction of the spins. Right? The spins interact with each other. Interact with each other. three types of phenomena that are being found, that are seen in materials. One is our ferromagnetism. Another is our anti-ferromagnetism. Another is ferrimagnetism. Now, what is the energy that is binding these spins, right? So the energy that is binding and the main energy that defines this why spins are up in one orbital, down in another orbital, that is given by exchange interaction. Or in other words, the exchange energy, right? So what actually is this term? Where does this come from? For that, we need to write the quantum mechanical state of an excited helium atom. Right? So, in helium atom, we have two protons and two electrons and neutron. So, let's just focus on the electrons. Right? So, where does this come from? Why this defines our these three: ferromagnetism, antiferromagnetism, ferrimagnetism. Right? So, how does the exchange interaction defines our these three phenomena? So, let's say I have a helium atom, two protons, electron, two electrons, right? Which is 1s2. Now, this is in ground state. Now, if I go to excited state, what happens? So, my electron can be in 1s. One electron can be in 1s, another electron can be in 2s orbital, or one electron can be in 1s orbital and second electron can be in 2p orbital. Right? These two are the cases. It can be either in 2s or it can be either in 2p. Now, what is the zeroth order energy? I mean, what is the ground state energy? The energy is given by its simple equation, that is half mc square alpha square into z square of 1 minus n1 square minus 1 minus n2 square. That will be equals to minus 68 electron volts. Right? You will get to the calculation. Slides. So now, what is our quantum state? 1, which is 1 0 0. No, it's nothing but the quantum numbers. One is n principal quantum number, it's azimuthal quantum number, and is a magnetic quantum number. So there are three quantum numbers. They're just for 1s electron, which has L equals to 0, which in turn gives us ML equals to 0. So n equals to 1, so 1 0 0. The next one is 2. I mean, either it is 2s or 2p. So n equals to 2, right? Then L. We don't know the azimuthal quantum number. Why? Because whether it can be S, which has 0, or it can be P, where L equals to 1, right? And ML. We don't know whether it is 0 or it is three different values, right? P or Px, Py, Pz, right? We don't know. So this is our quantum state. Now, this is for only the spatial distribution. Now, what about the spin? So, there is another term that is coming here. So this is for the spatial distribution. Another one is the spin. How do we write it? We can have two cases. Whether in one case we can have spin up and down, or in another case we have both the spins are in this direction, right? So one is alpha, beta. I mean, one electron is plus half, another is minus half, or the first electron is minus half and another electron is plus half. Here comes the symmetrization postulate. Now, symmetrization postulate has a very deep understanding, but for simple understanding, it can be approximated to if our spatial distribution function or the spatial wave function is symmetrical. Let's say if I have 1 0 0 and 1 0 0, that is symmetrical, right? What about here? It is non-symmetrical, right? So either we have, let me write it. So our quantum state will be 1 0 0 1 0 0, this one times 2L ml, this one, and function is plus, or the electron can be in 2L ml or 1 0 0. Right? This is our spatial function. And what about the spin? Spin is, it can be this or this one, right? This part is symmetrical, but not this part. So this is one quantum state, and this is also called as singlet quantum state. Singlet, it means plus half, minus half, going to the triplet quantum state. So that is the same, but the negative term will be here times cross. We have this one, and this one. So this is triplet side. Now, putting this into the Schrodinger equation and solving for the equation for the energy operator, then this will be equals to E square by 4 pi epsilon naught symmetrical 1 by r minus r naught symmetrical. Right? So this is for singlet, and this is to do for triplet, right? So I will be having the values of E singlet will be I plus J, and E triplet is I minus J, right? So now I stands for electrostatic interaction between the electrons and nucleus, also the protons, and or the electron-electron interaction. Now the J is the exchange integral term. Now the electrostatic interactions can be explained in a classical way, but the J term, which is coming, right, Es plus Ej will be Es minus Ej. The difference between the energies is 2J, right? That is not minimum value. That is a considerable amount of energy when compared to the I. So this exchange interaction, it cannot be explained in classical way. It is just a pure quantum mechanical. It comes from the symmetrization postulate. So again, we have to look through the parity operator. So let's not go deep into that. Let's just stick with the symmetrization postulate. If I have a spatial wave function symmetrical, then our spin function should be non-symmetrical. Because if we apply parity operator on bosons, which are the negative particles, the plus half spin particles, we will get a negative value upon applying. For example, if I have an electron reflection side, and if I apply parity operator, then I will get a negative sign on that. So the negative sign indicates it should be coming from either from the spatial wave function or from the spin wave function. So either the orbital or the spatial wave function can be asymmetrical, or the spin can be symmetrical, or either way, spatial is symmetrical or spin is asymmetrical. Now this excitation energy defines, not the excitation energy, this exchange interaction energy defines the which type of spin, whether it is singlet or triplet, which type of spins can be taken place, right? Or which type of spins are allowed. So if I draw the energy diagram for a helium atom, which is for our ground state is minus 68 electron volts. So the next state is either I have a singlet, right? If I represent it for 2s, then I can have a singlet or I can have a triplet. And because we have seen for helium the triplet is more stable because I minus 0, so that is more stable when compared to singlet, right? That's why when an electron jumps from 1s orbital to 2s orbital, they both have either up spins or down spins, not the up and down, right? The combination. That is not the case in the excited helium atom. So what is the difference? Difference is the value of closure. Now this defines the ferromagnetism. Now what is ferromagnetism? In paramagnetism, for example, if I have a body that contains the spin, as I said before applying magnetic field, the spins are random because they are not interacting with each other, so they are random. They can take any direction. Once we apply the magnetic field, they will align to that magnetic field, right? Because of the Zeeman interaction. To reduce the energy value, they align to the magnetic field. That is the case for a paramagnetic property. But what about the ferromagnetism? The ferromagnetism, it has some intrinsic magnetism. Now, how? So ferromagnetism comes from the d block elements, where again there is a different term that defines why the spins are like this, but let's not go deep into that. Let's just stick with the exchange interaction one. It can be very much equated to the Ohm's rule, right? Why the spins cannot be why, for example, to calculate from plus 2 onward, where we studied the d block elements, right? Where we try to find out the magnetic moment from d elements. So depending upon the d orbital, for example, a scandium, it has a d1, right? One electron is there. Scandium, vanadium, one electron keeps on adding into the orbitals, but we never asked ourselves why all the electrons are spin up, why cannot electrons can spin down, right? So for that there is another term called endless coupling. Let's not go into that, but the simple thing that defines here is the Ohm's rule, right? Now the electrons keep on adding into the orbital. So yeah, what does the ferromagnetism? How does the ferromagnetism come from? Because the spatial functions, right? For example, it has dx, right? This one has dyz, and this one has dx square minus y square. One is dzx, another one is dz square. Now, all these orbitals are not spatially symmetrical. Right? Dx square y square is different when compared to dxy, and dxy is different when compared to dz square. So our spatial wave functions are asymmetrical, so that rule is satisfied here. Now what about the spins? The spins cannot be asymmetrical. If our spatial wave function is asymmetrical, our spins also get asymmetrical, then that wave function will have a positive value. So it does not satisfy the symmetrization postulate. So the spins must be symmetrical. That means if our spatial wave function have asymmetrical, then spins must be symmetrical. That means all spins must have plus or down spins. So that's how the ferromagnetism comes from. In classical magnetism, it was more explained through the Weiss theory. It is a mean field theory where they approximated all the fields in like average out, taking the average out all the fields from the atoms inside a material. that is Weir's theory, that is more towards the statistical mechanics. So the excitation energy comes from the quantum mechanical explanation, and in Weir's theory they explain there is some unknown field that makes the electrons, that makes the spins to align in a certain direction, but that theory can be more explained with the excitation, so not excitation, the exchange interaction. So that is about the ferromagnetism. Not what about the antiferromagnetism? In antiferromagnetism, we have spins. No, let's not draw in orbital fashion. So suppose this is my material. In ferromagnetism, we have spins like this, and some spins in different direction. So they have inherent magnetic action because of the exchange interaction. So that's just I have explained before. So one spin will make sure the other spin looks the same way like the first. That is about ferromagnetism. Now coming to antiferromagnetism. One spin will make sure the other spin interact in such a way that the other spin has a negative half value. I mean, it is in south direction, plus half minus half. So the total magnetization value is 0. Why? Because the magnetization coming from plus half minus half, they are cancelling out. That will come out to be 0. Same coming to ferromagnetism. What happens in ferromagnetism? In ferromagnetism, same as in ferromagnetism, antiferromagnetism, but the magnitude of magnetic moments are not equal. Still, one spin interacts in other spin in such a way that the other spin is in opposite direction. I mean, if one spin is plus half, the other spin is minus half. That's how it is done in antiferromagnetism. So we have some magnetization here. Right? The only time the magnetization is 0, that is for antiferromagnetism. And again, there is a temperatures, like Curie temperature for ferromagnets. After that temperature, the ferromagnet starts to behave as a paramagnet. And again, for antiferromagnets, there is a nil temperature. After that temperature, they again start. There will be some residual magnetization, because the spins try to align in certain direction, and again they try to behave as a paramagnet. So that is all about the spin interaction. And there are other types of magnetism. There are band magnetism. There are different types of magnetism that come into picture. The band magnetism, to understand the band magnetism, we have to understand different things. One, we have to understand the chain model, the Ising electron model. Ising electron model is nothing but the electrons are freely moved in a metal or in any material, which is the case for metals, where the electrons are loosely bound. Valence electrons are very loosely bound. Right? They can freely roam in the material. So we need to understand that model, and from that model we can understand the chain model and one-dimensional chain model, from chain model to Hubbard model. So there are different things to understand, but to understand the band magnetism, we need to first understand how the density of states is taken, how the orbital shape is taken, how the electrons gets filled in an orbital. So for a simple explanation, for example, the magnetic moment of Fe, it should be coming from 4 μb, right? But instead from 4 μb it comes 2.2 μb. So why? For example, if I take Fe plus 2, right? So I have, this is my d orbital, and because I have 4 electrons, it should be 4 μb, right? But instead of 4 μb, that is, for example, 4 μb, it is not 4 μb, it is 2.2. Now why this fraction comes? That is called band magnetism. Now what happens in band magnetism? So why it is coming? why it is coming that value, right? So that's our question. So for example, if I saw the orbital, right? So let's say a parabolic curve. And because we're talking about bulk materials, we have a continuous distribution of electrons, and the same goes for this. This is for positive half, this is for negative half of electrons. So when I apply the magnetic field, and because of the zero interaction, this will shift. Now this is my Fermi energy. Say this energy is my Fermi energy, right? And because of application of magnetic field, this will shift upwards, this will shift downwards. Now we can even represent what is the amount we are shifting, right? So that total amount shift is 2 times of mu v, right? The plus mu v comes from here and minus mu v comes from here. The total shift is this, and whatever the electrons, and this is my Fermi energy. No electrons are above the Fermi energy, but here there is certain concentration of electrons, number of electrons that is above the Fermi energy. And this is the reason why, because if we do the integration and we find the total value, then the total value will be 2 mu v. That is the case. Now, if you are talking about the nanoparticles, so once we go down the dimensionality, this density of states starts to break, right? So I have discussed before, I have proved how the density of states changes with energy. It is GEE, the number of density states, the number of available energy of states per electron per unit volume. Right? So if I try to write it like that, then my energy value like this, it will come like this. It is a continuous band, there is no breakage, right? Because the bands or the electron bands or orbitals overlap and form bands. So again, I'm not going to talk the previous topics. So this is for 3D, and coming to 2D, what happened? With 2D, it turns out to be like this, right? No. We had like this, we had steps, because G doesn't depend upon the energy, right? The number of density, the probability of density of states per unit volume didn't depend on energy for 2 dimensional. And for 1 dimension, we had, there is a peaking and then again dying of the function. Again there was a peak and again dying of the function. So that's how for 1 dimensional nanomaterials. For 0 dimensional nanomaterials, it was a discrete. There was so much discretization. There was spread in the energy levels, the density of not the density of states, the energy of the system energy that can be taken into account. So that is it. That's all for the density of states and the magnetism coming from different particles. So now coming to this one. And that means, for example, if I take a material, in a material we have, let's say, the polycrystalline grains, and inside a grain we have domains, and the domain, there is this thing like crystallite is, and if you are talking about the diffraction, in terms of the diffraction phenomena, the crystallite is nothing but how do you say, a coherent scattering domain. The same goes for the domains in the magnetism. In a domain, all the magnetic spins are aligned in a certain direction. Let me write this once again. This is my material. This is my grain. Inside a grain, I have domains. inside the material there are different domains. Now, in each domain, the spins are pointing in a certain direction, right? So this is, in each domain we have the spins pointing in a certain direction. So now for example, if I take two domains, how the spins are going to change from one domain to another domain, just like the case in a grain. If suppose inside a grain we have one direction, the atoms are arranged in certain direction. For example, if I take two grains, this is grain 1 and grain 2. Let's say the atomic planes are arranged like this. So the triple one one direction is this direction, and grain 2 atomic planes are arranged in different direction. For example, the 1 direction is in another direction. The same goes for the domains. And at grain boundary, we have the different orientation of atoms. Like the more or less, the atoms are arranged random in the grain boundary, right? So the same goes for the domain. So now, what happens at the domain boundary? So we define a term called a wall, which is a block wall. Now what happens in the block wall? In block wall there is a different orientation of atomic spins. So this is a good representation what happens. This is one domain and this is another domain, and this dimension is our block wall, right? And it can be about 100 lattice constants. Right? And this distance can be 100 lattice constants. So now this block wall will define again when the coercivity. Not the coercivity, it defines the anisotropy, right? So how it defines the anisotropy? Right? Now, thicker the block wall, one, thicker block wall, two, thinner block. The thinner block wall has the high anisotropy values. So the NDF, the ND magnets, they have thinner block walls. So they have high anisotropy, but when it goes for the thicker block walls, now the block wall will have the extra energy associated with it. The same goes for the grain boundary. Grain boundaries have extra free energy, right? The more free energy when compared to the bulk wall, right? Because of the surface, the extra free energy. The same goes for the block wall. The block wall will have the extra energy. So the thicker the block wall, the higher is the energy of the system. Now if I apply the magnetic field, because already there is a present of the present of the higher energy, more energy. So one is from the energy from block wall. The another way is the energy from the Zeeman interaction, right? So the block wall will increase the total energy of the system. Now if we apply the magnetic field, the spins will try to align in the magnetic field direction to decrease the energy, because one energy is coming from energy block wall, another is coming from Zeeman block wall. The Zeeman interaction, so the system of the energy shoots up. So what the system tries to minimize its energy. So spins will try to align in the magnetic field direction. So there is a less anisotropy. But what happens in our thinner block walls? So thinner block walls, because the energy is very less, so even upon application of zero interaction, the energy of the system doesn't shoot up as much as compared to the materials with thicker block wall. So the thinner block wall materials have high anisotropy. That is the correlation between the anisotropy and block walls. That is about the block walls. Now there is another called the anneal wall. Now the basic difference between the block wall and anneal wall is the magnetization goes zero when going from one domain to another domain, but in anneal wall the magnetization doesn't goes to zero. It's more or less can be described with the help of a spin wheel, just like what do we call the phonons, right? The atomic motion, the atomic vibrates, right? The one atom vibrates and that atom is linked to the other atoms, right? With the coordination, with a certain coordination number. So there is a wave that travels from one point to another point. The same goes for the spins, and because of the exchange interaction, each spin is correlated, in connection to the another. So if one spin tries to change the direction, that will have an effect on the other spin, and if that spin changes direction, that this effect will go on moving just like a wave. So that is again the different topic, that is a spintronics. Again, let's not go deep into it. So that's more can be explained from wheel code. So the next one is that's all about the block wall. Now the next point is the MH curve, right? Now to know, there are two important parameters that defines the magnetic material, where the application of the magnetic material. One is our coercivity, which is Hc, which can be represented as Hc, and the other is retentivity. Or people even called as a remanence. Right? Now, what is an MH curve? It is a basic characterization technique to find the magnetic property. Right? So, suppose if a material, let's say this is an iron material, so what I do is I apply magnetic field and apply H, and I measure what is my magnetization, what is the response of that, what is the response of the material with respect to the magnetic field, right? Now that is my MH curve. Now there are different measuring instruments. One, it is VSM, and another is squared. Now VSM is vibrating scanning magnetometer. What does it do? It applies magnetic field and it vibrates the material. When due to vibration, there is again the Faraday law of induction. Because of the material is vibrating, because of that we'll have an electric field generated. So for example, there is a static magnetic field, and if I vibrate my material, that means the material is going out and going in, and because of that there is a formation of our electric field, generation of electric field. It is based on Faraday law of induction. So this electric field is again taken through some rectifiers to amplify the signal, and this signal is displayed, and this is our magnetization, right? So that is the main principle behind VSM. So that is our MU versus H. So how does it look like? So for example, let's say our magnetic material has a zero magnetization. Now I apply the magnetic field, so it starts increasing. It starts from zero. It starts increasing, and it reaches the maximum value. What is the maximum value? That is the saturation magnetization. Now again, what does that mean? The my saturation magnetization, nothing but the maximum magnetization that can be obtained from any material. So what happens there? All the magnetic moments try to align in one direction. Right? So that is my MS. And once I start to decrease H value, I will have a reminence. I have a magnetization. And if I have magnetization, I'm talking about the ferromagnets, right? So if my M gets to 0, then that is a paramagnet. So if I have a MR or HR, so conductivity is represented as MR or HR because it is reminence, right? So again, I keep on decreasing my H value, not typically decreasing, it's just a changing direction of H. So that will go like this, and I reach a point where my H is 0, and that is my coercivity. What is my coercivity? Coercivity is nothing but the amount of magnetic field or reverse magnetic field that is required to make the magnetation of any material to 0. In negative direction, again I reach my saturation magnetization. So again I change my magnetic field direction until again came on here and it will go. So this is famously called as the MH loop. So there are 4 quadrants. So this is first quadrant, second quadrant, third quadrant, and fourth quadrant. And the area under this curve will give the energy product, right? So depending upon this, we characterize the magnetic materials as 2 types. One is a hard magnetic material, the soft magnetic material. If I have a large coercivity values, then it can be called as a hard magnetic material. If I have a small coercivity values, then it is called as soft magnetic material. What does it mean? We need not to apply high amount of magnetic field to make the magnetization 0. So soft magnetic materials are used where to minimize the energy losses, right? Used in transformers, soft magnetic materials. And hard magnetic materials are used where we need the anisotropy. For example, storage, right? To maintain spins in a certain direction, not to change the spins in another direction. So that is about this. And another, how we generate magnetic fields and magnetic fields generate from solenoids, I have explained in previous lecture. So that is about the hard magnetic materials and soft magnetic materials, right? So now, for example, if I have a magnet and it is in a magnetic field, now what are all the energies of the system? Suppose if I have a magnet of a cube, then what is the total energy of the system? The total energy of the system, the total energy of the magnet is equals to 1 is coming from excitation energy, right? What is the excitation energy? What is the another one? Another one is the anisotropy energy. Another one is magnetostrictic energy, magnetoelastic energy, magnetostrictic energy. And this magnetoelastic energy is more mostly can be seen in oxides, right? Because of the orbital overlapping, the bonds try to stretch, right? Because of the magnetic moments, the bonds, for example, in oxides, let's take square bipyramidal. Let's say if I have an atom here, right? So it has its own orbital, molecular orbital, and these have their own molecular orbitals. Right? I shouldn't say molecular orbital; it's atomic orbital. Now, because of overlapping of orbitals and the interaction of spins, these try to stretch. So that is coming from magnetoelastic one, right? That is coming from term 3. And the final term, let me write it here, the total energy is the excitation energy plus energy from anisotropy plus the energy from magnetoelastic, magnetostrictic. The third term, which is Zeeman interaction. Visible interaction is nothing but the external field, the interaction with external field. So this is my total energy. Excitation energy is coming from purely quantum mechanical model, so which can be easily taken from, which can be approximated to Moore's rule. So then the next one is our anisotropy. Anisotropy is coming from the grain orientation, orientation of domains and domain walls, block wall. And the third one is the magnetic velocity because of the overlapping of orbitals and the spin interactions. And the final one is our visible interaction. Visible interaction is nothing but it's not from the intrinsic, it is the external magnetic field. That's all. This is the total energy of any magnet inside a magnetic field or any other field. Right? Even it is an electric field itself creates a magnetic field, and that magnetic field again interacts with our spins. So that is all from the magnetism part. That is all from magnetism part. So we have seen different things. Let's stop the magnetism part here. Now moving on to the optical properties of nanomaterials. So yeah, going to the optical properties. Again, what are the things defined? Sorry, coming back to the magnetic materials, I forgot to explain one last topic. How our coercivity changes with respect to the dimension of the nanomaterial, right? So this is my coercivity and this is my size of the nanoparticle. Right? The size of the nanoparticle. So it actually looks like this. And there is some critical size to which the coercivity increases and after that decreases. So you can call it as the size of the domain. Rather than the size of the nanoparticle, I can call it as the size of the domain. Or size of the material, that will be probably more better way of explaining, not the size of the domain. Now on decreasing the size of the material, so what happens, or the size of the domain, there will be more number of domains, increasing number of domains, right? So rather than one big domain, there are more number of domains, so there is more coercivity left because there is increase in coercivity. Why? Again, there is a block wall, right? The block wall model. Now what happens, and because there is more number of energy, right? More number of energy is required to spin the electrons in certain direction. So there will be more amount of coercivity, and because of the resistance from the domain walls, the spins remain in the same direction. So once we started to decrease the size of the nanoparticle, decrease of the system, what happens, once we reach a critical diameter, we have this region where the domains are non-interacting, right? So the domains become non-interacting. There is less resistance from the domain walls. So what happens? The HC starts to decrease. So because of less resistance from the domain walls, the domains will try to get into more randomized fashion. So we reach a stage where we reach the HC equals to 0. HC tends to 0 or approaching to 0. We call it as a super paramagnetism basically. So what does that mean? Super paramagnetism is nothing but, so when we apply magnetic field, the magnetization goes up, which has very low coercivity values, and also it is very not thermal resistant, thermal fluctuation resistant. Even the small thermal fluctuations can make can alter our magnetization value. So that is more related to superparamagnetism. It has very low what do you call recursivity values, right? So that is about superparamagnetism. There is another called in superparamagnetism. Once we remove the magnetic field, the magnetization will die down to zero, right? But not the case in superferromagnetism. In superferromagnetism, again, paramagnetism, the basic assumption is no interaction of space. In ferromagnetism, there is an interaction, the excitation, not excitation, the exchange interaction. That will make sure the magnetism doesn't go to zero, right? So that is the key difference between the superparamagnetism and superferromagnetism. One doesn't have the interaction between spins, one has the interaction between spins. One doesn't have the, there is no assumption, or there is no account of exchange interaction. One has the content of exchange interaction. So that is about superparamagnetism, superferromagnetism. That's all about the magnetism, magnetic properties of nanomaterials, coming to optical properties of nanomaterials. So again, what are the few things that I have to keep in mind? One is the quantization, or decreasing the size of the system. There is a quantization of energy levels. Right? Now the size interaction. Right? What do we mean by size interaction? Size interaction is nothing but the size of the material, or the size of the nanoparticle that is interacting with the external stimuli. That may be photon, electron, X-rays, anything. So size relation. Please keep in mind, this size relation plays an important role in terms of plasmons. In terms of plasmons, and also in terms of explaining in terms of plasmon resonance. Now, what happens to bands, right? What do you mean bands? The overlapping of orbitals in the metallic system or any other system, right? So, what do you mean quantization? Quantization is nothing but discretization. Discretization of energy levels. This I just have explained intensity of states. What happens to the allowable energy levels in three-dimensional materials? What happens to the two-dimensional, one-dimensional, zero-dimensional, right? For zero-dimensional, there is more discretization of energy levels. The density of state, there is more discretization, right? There is more continuous energy curve. The electrons have to stay in certain energy levels, right? So that is about this. There is this phenomena. For example, in some semiconductors at very low temperature, they emit they emit energy. They emit photons. Now, why that happens? Even below our band gap energy, right? So for what Einstein theory, there is a theory where the radiation falls on a material, it emits electrons, right? The photoelectron theory, right? Classical, which was explained by Einstein. So for example, if some radiation falls on the material, so that radiation is absorbed by the electrons, and the electrons, they may either shift into the conduction band, or they may even come out of the material. Right? So if we give an energy, for example, the band gap energy is 5 electron volts, and for example, if I supply 5.2 electron volts, what happens? So the electrons will try to jump from the valence band to connection. Or the what do we mean band? Band is nothing but again the overlapping of orbitals. So instead of discretization, there is a smooth. There are a range of values of energy levels where the electrons can occupy. So on application of the energy, right? So we're applying electromagnetic radiation, or what happens is on application of energy, this energy is taken up by the electron, and electron will jump from valence band to connection band. Right? Now, if an electron jumps from valence band to connection band, and electrons will move in conduction band, they can conduct, right? Which in turn defines our conductivity, the electrical conductivity, and seen in the semiconductors. Right? So, at very low temperatures, what happens? When electron moves into conduction band, it has a negative charge there, and it leaves the positive charge in valence band. And because of the electrostatic interaction, right? So let's say F equals to, now what is our electrostatic interaction force? F equals to Q1 Q2 by R square, or K. What is our K? K is 1 by 4 pi epsilon naught. So 4 pi is a value constant, and epsilon is the permeability. Right? So Q1 Q2 by R square. Now R is the distance between the valence band and the conduction band. Now Q1, Q2 are the charges. Now we know electron has -1 and hole has +1. So F will be equals to minus E by R square, or K minus K by R square, right? Now, minus K E by R square. That is a force that is attracting the electron and the hole, and that is we call it as a binding energy. Now, what does this binding energy do? The binding energy is an element which binds the electron and hole. Binds the electron and hole, right? So, which binds the electron and hole. Now, because of this, the electron can, because of this binding energy, which reduces the total energy of the system, so the electron can occupy other than energy state of conduction band, other than the lowest energy state of the conduction band. That means the electron, for example, this is my conduction band, this is my valence band. So electron can be found below the conduction band. Right? So, yes. So same goes for the hole. The hole can be found above the valence band, and the electron can be found below the conduction band. Right? This is my electron, this is my hole. So, now, here I have electron, here I have hole. Right? But for the ideal case, the hole should lie below the valence, the highest valence energy level, and the electrons which goes into the conduction band should have cannot be lie in the formidable energy. Yeah, right. But due to the binding energy of electron with the hole, the electrons and holes can be find in between or in the what do we call the forbidden energy, right? Now this is about the exciton, right? So it's the same. I will explain it again. So in case of semiconductor bulk materials, if an incident photon energy greater than the band gap of any material, an electron may excite it from valence band to conduction band, right? Now, if under these conditions, when atom try to relaxes, the photon is absorbed with the hole. Now again, the electron will come back, jump back to the valence band, and it combines with hole. It emits an electron. It is the ideal phenomenon that happens. But inversely, if an electron in the conduction band returns to the valence band and combines with the hole, a photon is released from the bands. However, at low temperatures for bulk semiconductors, there is an optical absorption below the energy level, as I said before. The electrons and holes can be, even if we supply the less amount of energy, right? Not supplying the band gap energy, even if we supply the energy less than the band gap energy, the electron jumps and to an energy level. So this process is associated with the formation of electron and hole bound to each other, right? Which is called as exciton. As for any other particle, the exciton has mobility, just like electrons, protons. The electrons have the mobility. Exciton has the mobility. It thus can move freely through the material. The binding between the electron and hole arises from the difference in charges, right? And I have represented the formula: F is equal to minus Ke square by R square. Sorry, Ke square by R square. Right? Now, the electrostatic interaction reduces the energy required for exciton formation with respect to the unbound electron and hole energy, which is a formidable energy gap, which results in bringing the energy levels closer to the convection band, right? Which I represented here. Right? And now, because of this, we have the different Bohr radius, right? Initially we had different Bohr radius between the valence band and the conduction band, right? It has a constant radius, difference in radius, but now it is different because the electron can take take energy levels in the formidable energy gap. Same goes for the hole. So that is about exciton. Now the difference arises when the exciton radius has a nanoscale dimensions. So, for example, if we take a nanomaterial, the exciton's radius for nanomaterials, the exciton radius is confined, just like the energy values, right? In terms of bulk metallic materials, we have a continuous band, but for nanomaterials, this continuous band will get discretized. We have an exciton level, energy level, right? So, what are the consequences of this confinement? The effects of nanoscale on optical absorption are more associated with the density of states in the valence and conduction band. The quantization of energy levels in nanostructure influences the exciton effects. So, now, as the nanomaterial changes from 3-dimension to 0-dimension, when quantum confinement is more severe, the density of states will get quantized and the material shift towards the higher energy level. What do you mean by higher energy level? Because of the discretization, even in 1 dimension, the particle in 1 dimension, there is a formula which is inversely proportional to L square. So it is due to discretization, the energy of electrons, the average energy of electrons will increase, right? So as a result, we have the blue shift that is expected in the absorption spectrum as the size of the nanomaterial decreases, whereas the red shift occurs for the increase in size. This is visible, which shows the absorption spectrum of lead sulfur nanoparticles or lead selenium nanoparticles. Again, finally, the higher absorption peak shows are associated with the formation of excitons, which shift towards the lower wavelengths, right, with decreasing the nanomaterial size. These peaks are shifting towards the lower wavelength, right, because of the discretization, digital states, all the things are happening. So we have a blue shift, and this peak is because of the excitation formation, so exciton formation. So to understand more deeply the influence of excitons, two regimes of confinement might be identified, namely a weak confinement and a strong confinement regime. The weak confinement regime, there is a correlation between, let's say, weak confinement, weak C, strong confinement. Now, in weak confinement, the dimensions of the nanomaterial are greater than the exciton radius, right? So there is a correlation. So then the electron and hole are a correlated thing. Under these circumstances, the Coulombic interaction between the electrons and the hole leads to increase in the exciton binding energy. This causes a shift of the exciton peaks towards the blue. That is the reason why this peak shift towards the blue. It happens in terms of the weak, confinement. Weak confinement means the size of the nanomaterial is greater than the exciton radius. So because of that, the electron and hole are correlated, and which in turn increases the binding energy. So this binding energy will shift because of this increase in binding energy, this will shift. This will have a shift on peak from higher wavelength to lower wavelength, shift of blue shift. And for strong confinement, the size of the nanomaterial is comparable or less than the exciton radius, and because of that, the electron and hole are not correlated, right? And the electron and hole become independent and they move freely inside the convection valence band without the binding of both of them, right? Now, in addition to these semiconductor nanomaterials, the optical properties of metallic nanomaterials are also affected by the nanoscale. So a good example is the gold nanoparticle. Now, a gold nanoparticle appears yellowish in color in bulk form, whereas the nanoparticle of gold gives a color of a ruby red, purple, and other color, for example blue color, depending upon the nanoparticle size. To explain why this happens, so there is this physical phenomena that happens, that is called as the plasmons. Now, I have explained in first few lectures, first or second lecture, what is a plasmon, right? I have described different quantum particles like phonons, bosons. What are phonons? The current oscillation, the current oscillation of atoms inside a crystal lattice. What about the plasmons? The plasmons are nothing but the current oscillation of bosons or the electrons, right? So plasmons is nothing but the collective oscillation of electrons. There are two types of plasmons. One is the surface plasmons and the bulk plasmons. And this type of changing color depending upon the size of the particle is well explained with the help of the surface plasmons. So from this surface plasmons, there is a phenomenon that happens which is called as SPR, the surface plasmon resonance. Surface plasmon resonance. Now there are three terms: surface, plasmon, and resonance. Surface is nothing but the surface property, or the area which exposed to the other medium, right? Now, what is a plasmon? It's a collective oscillation of electrons. Resonance is nothing but oscillating on the same frequency. For example, you have two tuning forks. One is vibrating at 5 Hz, another also is vibrating at the 5 Hz, and no, sorry, not the 5 Hz. For example, if I have one tuning fork, and if I try to vibrate it at 5 kilohertz, and if I take it near to the another tuning fork, at a certain distance, it also starts to vibrate at the same frequency. Now we call it as a resonance, because the two materials are oscillating at the same frequency, right? So that is termed resonance. So when electrons falls onto the surface atoms also contains electrons. So when this frequency of the radiation that we are trying to emit, let's say this is my surface, it has the surface atoms, and the surface atoms has electrons, and if I incident some photon or electromagnetic radiation, what happens, right? If I emit some radiation onto the surface, what happens? So let's say the emitted radiation, the bombarded radiation, has a frequency mu. Now this frequency starts to oscillate the atoms, which creates electric fields, and which oscillates the electrons, right? And this collective oscillation of electrons in resonance with the frequency of light will result in the formation of surface plasma. And because of these oscillations, we have positive and negative charge that is created, and this positive and negative charge will result in the formation of emission of photon, right? Which is nothing but an electric field. And this electric field, now the photon is nothing but the oscillating electric field. There is also the magnetic field which oscillates in perpendicular, and from Maxwell's equation it is proved that if we have an electric field, there is a magnetic field that is oscillating in perpendicular direction. So electric field and magnetic field cannot live with each other. So that was described from Maxwell's equation. That's why no one dared to there is this word, there is this phrase, no one dared to mess with Maxwell's equation. So that's true. Most of the time, no one tries to mess with Maxwell's equation, because it tells the basic theory about how the electromagnetic radiation is made up of, the oscillating electrical magnetic fields. So that's about it. Now, coming to this, to how to explain this effect, we need to understand the physical phenomena of plasmons, and we know the plasmons are quantized waves propagating in materials through a collection of mobile electrons. So the collective oscillation of electrons, nothing but the waves. So waves travels where there are two types of these traveling waves. One is the surface plasmon discretized energy wave, and there is a bulk surface plasmon wave that travels through the medium. Now, let's come to back. The plasmons are readily observed in noble metals, like the d bands of electronic structure are filled, such as gold, copper, and silver metals, magnesium, and aluminum. The plasmon can exist within the bulk as well as on the surface of the materials, of the metals. Among these, the surface plasmons are most relevant for what? Yeah. Most relevant for nanomaterials. Surface plasmons have lower frequencies than bulk plasmons, and thus can interact with photons. Right. In fact, when photons couple with surface plasmons, alternating regions of just like I said before, when photons interact with the electrons, just like I said before, because of this, the alternating regions of positive and negative charges are produced in the surface of the material. See, I have so this is my surface. There is positive, negative, again positive, negative. So alternating positive and negative charges are produced in the surface of the material. Therefore, which generates an electric field. In conventional words, the surface plasmon polarizations are essential light waves that are trapped on the surface of the material as a result of interaction between our photons and incident electromagnetic radiation and the existing free electrons. Right? So, even though there is an interaction between the photons and the surface photons, sorry, not the phonons are atoms, the surface plasmons. I repeat myself. Despite the due to the interaction between the photons and surface plasmons, there is a creation of oscillating positive and negative fields, which is nothing but the electric field that is trapped in the surface of the material. Now, even though the interaction, the surface cannot emit this electric field. So, for that to happen, so it is not possible in flat surfaces because it just traps it. Now, therefore, to cause the change in momentum, now why it doesn't happen? Because the momentum of light is different from the momentum of surface plasmons, or the momentum of electromagnetic radiation is different from the momentum of surface plasmons. So, therefore, to cause the change in momentum, a thin layer of metal is placed between the two materials. Okay. Suppose this is my thin layer of metal that is placed between the two materials. Right. So, depending upon the different refractory indices, the angle of incidence will reach a critical value where it just reflects. Right. If this is my incident, and upon some critical value, this incident will reflect back. That is called as a critical angle, right? And this can be this can be more changed with the refractory indices. The another technique is to induce surface plasmons is to roughen the material surface. So now the surface plasma polarizations can be used to cause extraordinary transmission. This is a phenomena where the thin metallic film which traps because of the oscillating positive and negative charges, there is a creation of electric field. This electric field can be transmitted through on the surface. Right? So this is very specific to the size and periodicity and can transmit more light at certain energies than anticipated. Moving on to the another type of surface plasma, which is relevant to the nanoscale, consists of localized surface plasmas. Now, again, what is localized surface plasmas? So, to form the localized surface plasma, one necessary condition to form localized surface plasma, what do we need? There is one condition that needs to be satisfied. The wavelength of the incident electromagnetic radiation should be greater than the size of the nanoparticle. This is lambda size of nanoparticle. So If this occurs, the electric field of the incident light can induce electric dipole or the dipole in the metallic nanoparticle, right? So if this is my nanoparticle, suppose this is my nanoparticle, and because of the oscillation of the electric field, the electromagnetic radiation, it creates a dipole, right? It induces the dipole on the nanoparticle, right? The wavelength of the light required to induce the generation of localized surface plasmons depend upon the size of the nanoparticle as well as the shape and composition. Normally, as the particle size decreases, the plasmon frequency increases, or the wavelength of the light decreases, leading to the blue shift in the spectrum. However, for the case of spherical gold and silver nanoparticle, their plasmon wavelengths do not cover the entire visible spectrum. Thus, nanoparticles with different shapes are required, although the non-spherical geometries are much more difficult to attain. So that is how we get different photon emission depending upon the size of the gold nanoparticle. The photon emission, it appears to blue, sometimes yellow, green. So, for example, if I take the cadmium selenium quantum particle, cadmium selenium quantum dots, it has different colors depending upon the size of their nanoparticle, the quantum dot, right? So it can change from blue to green to yellow to orange to red, right? So depending upon the size and due to this localized surface plasmon, they emit different wavelengths of electromagnetic radiation. So this is about the optical properties of nanomaterials. I will stop here, and the remaining the properties. Right? If sir have enough time, we can discuss the acoustic properties. There is not much about the acoustic properties of nanomaterials because the acoustic waves, the sound waves, have very much larger wavelength when compared to the nanomaterials, right? The acoustic waves can range from wavelength can be ranging from 1 meter to 1 centimeter. It can be it can have very high wavelengths and very low frequencies. So it does not have much effect on the nanoparticles. So the next session, sir might discuss special cases about carbon nanotubes or the carbon nanomaterials. So until then, if you people have any doubts, please ask now, or you can even ask you can even post your questions in the NPTEL website of the Nanomaterials course. So thank you. I will stop the recording, and if anyone has doubts, you can ask.